cis310. Okay, I can see maybe half the class is here. Okay, I'm assuming the other half is busy working on the program.
Well, they kind of ran out of time by now.
Yes, exactly. All right, so let's switch gear and talk about cisp310, and I will give you the solution. I know most of you found the solution anyway. Okay, you'll figure out how to work this out, but I will give you the solution anyway, and I'll show you how I will work on it. Okay, because this is definitely a problem-solving type of homework assignment, and not one of those, follow step 1, 2, and 3, and you'll get the result kind of homework assignment. I would never give those homework assignments to you.
We know.
All right, so let's go back to
Somebody's got a question.
Egg Hunter. Yep, go ahead.
Can we turn on we can't hear you over here.
Okay, I just turned it on. Thank you. See, they should not put the switch here. They should give you guys the switch, make it a Bluetooth switch, so you can use your phone and just click and go like, okay, now we turn on text microphone.
You have volume control on it as well, in case you're not loud enough for people in the back.
They can make it an automatic feedback thing, so they can have monitoring microphones at the back of the classroom. They can adjust the gain, depending on whether the voice recorded here and what is over there is consistent or not. So when you guys start to have chatting and stuff like that, then it will just crank it up until my voice is 80 decibels over yours. So if yours is 50, then the whole system will have like 130 decibels, which is deafening. I'll be having my buffs. All right, so let's work on the homework assignment. I believe I have it downloaded and expanded already. Okay, it's not about OB1 anymore. So we switch gear and talk about Egg Hunter. So go to downloads. Go take a look at, oh, I guess not, the parent folder. There we go. And this one has the answers already, so let's get rid of the answers. And by the way, I actually accidentally displayed the answer for, I didn't measure, maybe half a second in the previous class. How many people note that and actually remember the correct answer because I just flashed the answer for half a second? You did? Okay, very good. But most people did not pay attention.
No.
Okay, so let's work this out. Okay, let's work this out. Okay, the objective. Okay, the objective is I want EBX to have a particular value. Okay. So we start with this value, which is supposed to be in register EBX. You look at this number and go like, well, there's no way I can relate this number to the dot byte, the dot word, and the dot long. Because this number is currently in base 10. Okay, it doesn't have any prefix. It has no 0 in front of it, which is the octal prefix. It has no 0x in front of it, which is the hexadecimal prefix. So without any prefix, it is a base 10 number. Does base 10 number play well with binary bits, bytes, and words? No. Okay, there's no boundary. Okay, they don't match up the boundaries. So the first thing you need to do is to turn this number in base 10 into a number that we can do with more easily in base 2. You can use base 2 if you want to. This is a 32-bit number. It's kind of long. You can also turn it into hexadecimal, okay? Because in hexadecimal, every 2 digit is 1 byte. Can someone tell me why every 2 hexadecimal digit is 1 byte? Go ahead.
So each digit is 4 bits.
Exactly. So 1 hexadecimal digit represents 4 bits because you can go from 0 to F, which is 0 to 15, and you can use 4 bits to represent those values. So if 1 hexadecimal digit is 4 bits, 2 hexadecimal digits will be 8 bits or 1 byte. And a byte is very easy to handle because we are dealing with a byte addressable architecture. Okay? So that means if you display this number in hexadecimal, that will give you the most convenience when it comes to solving this problem. Okay, so that's the first thing you need to do is to turn it into a base 16 number.
Once you turn this into a base 16 number, you will recognize some of those digits can be found in a dot by dot word and the dot long, but not in the order that you want, okay? Okay, let's do it one step at a time. So what I'm gonna do is I am going to comment out of these 4 lines, okay? And I will actually go ahead and assemble, link, and debug the program. Even though I have no code to execute, I can still examine memory locations. So that's the first thing I will do. Okay. So we'll do ASGStabs-O, funny.O, funny.S, link to funny, funny.O, GDB, funny. Do a list. We don't even need to list it, we just have to set a breakpoint. B_start. We just set a breakpoint at the very beginning of this program and run it. Okay. Remember what I said here, let's convert the number into base 16. And some people say, well, I don't have a calculator that can convert into base 16. You don't need one because you have GDB, okay? You have GDB. You say, okay, so you say help, okay? Help will bring you up, and say, okay, what kind of commands do you need help with? I want help with aliases, no. Breakpoints, no. Data, maybe. Files, no. Internal, no. Obscure, probably no. Running, no. Stack, no. Status, no. Support, no. Trace points, no. User-defined, no. So the most likely one is data. So you say help data. And it shows you everything that you can do, you can display data with. So there's the agent printf, append, dump, and so on. So this one is print, okay? What does it say? Print value of expression exp, okay? So maybe that will do it. So you say help print, and help print says, print value of expression exp, blah, 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 and so on. And then it says here, exp may be preceded with /fmt, where fmt is a format letter, and it says cx command. Okay, then you say help x, and x says examine memory location. And then fmt says right here, you can display in octal, hexadecimal, decimal, unsigned decimal, and so on and so forth. But you don't even need to go through all this stuff here, because I cannot remember which day, but I remember I displayed memory locations in bytes in one of the classes. Okay, where was it? Yep, /x. Yep, that's the x command. But you can do the same thing with print. So I want to list the program again. Just look at this number, and I will do a copy. Say print /x, which means print the following expression in hexadecimal. So we do a paste, that, that's the return key. So now I have the hexadecimal representation of the bit pattern that has to end up in EBX. Okay? If I'm doing this homework assignment, I would probably put this on a piece of paper because I need to refer to this hexadecimal number from time to time. Okay? Which I can probably do here, and I can just use, well, let's see. I can use notes, which is kind of like a post-it. So I'll just use my post-it to remember 0x17001221C. Okay, now the big question is, if this is going to be the hexadecimal representation of the bit pattern in the register EBX, which one is the most significant 2 digits? Can someone tell me the most significant 2 digits of this number? 17, exactly, okay? And according to Little Endian standard, the most significant byte should be at the highest address, okay? So you have to remember that part, okay? All right, so given this is the actual content of EBX, so now we can try to answer the question. Out of the 4 instructions that you can, well, out of the 3 instructions they can play with, but there are 4 instructions in question,
which one is the only one that can change the most significant part of this number? We can still see those instructions here even though they're commented out. So which line is the one line that can put the 1700 into EBX? Line 9 and line 10 together. Okay, line 9 is the one that controls the location, but line 10 is the one that actually puts the bit pattern into EBX. Okay.
We don't change 10 though.
Sorry?
We don't change.
You cannot change 10. Yes. Yeah. So line 9 and 10 will be the ones responsible to put the 1700 into EBX because no other instruction has access to these 16 bits. Okay. Let's take a look at all the instructions first. This instruction only changes EAX. It doesn't change EBX, but it does set up the stage to change EBX. This instruction, on the other hand, does change EBX as a 32-bit register. Okay, so we'll keep that in mind. This instruction will only change the least significant 16 bits of EBX. It doesn't affect the most significant 16 bit of EBX. This one only changes bit 8 to bit 15 of EBX. It does not change anywhere else in EBX. So your only chance to put the 1700 into EBX is this instruction, and the one before that would set up EAX so that we can get it done. Are we doing okay so far with the problem solving part? Okay. So now you look at the initialized memory and go like, okay, I'm looking for 1700, blah, 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 and there's none over there, okay? I don't see a 17 anywhere from line 2, 3, 4, or 5. So what do I do? Well, we look at these values and go like, okay, maybe it's in the wrong base, okay? Because that 17 is in base 16, it is in hexadecimal, and these numbers are specified in different bases. This is 12 in base 10, this is 34 in base 10, this is 23 in base 10. And guess what? 23 in base 10 is 17 in hexadecimal. Is that okay? Then we will think, oh, maybe we just need that byte over there. But that's not, but you cannot just take one byte. You have to read 32 bits, put all 32 into EBX to get to the most significant 16 bits of it. So the next thing we should do is to take we want to look at the memory layout. In other words, we look at lines 2, 3, and 5, and then we want to figure out, okay, exactly what type of bytes do we have stored in memory. Okay, that's what I will do next. But I can do it here inside the debugger. It's already running. It can display that. But instead of doing that, I'm going to switch to my little notepad here. It's kind of like my Post-it. And we'll go ahead and try to figure this out by hand first. So doing this by hand, we'll start with line 2. Line 2 says dot byte 12, which is in base 10. In other words, how do I represent the value 12, 1, 2 in base 10 as 1 byte? Okay, how do we do that?
Zero, zero.
Just a 0C, okay, very good. 0C represents, so I'm not using 0x here because all of these are going to be in hexadecimal. So 0C is the first byte. The next one is 1, 2, but it's already in hexadecimal because of the 0x prefix. So there's no need to do any work with this one. Okay, where did that? Okay. Uh-oh. Where did it go? Just lost track of my, oh, there we go. There we go, okay. So the next one is 1, 2, but it is already in hexadecimal. And then we have the octal number 1, 2, because it starts with a prefix of 0. When you have an octal number and you want to convert into hexadecimal, you probably have to convert into base 2 first, and then regroup the bits in groups of 4, and then convert it back into base 16. So as an octal number, each digit is representing 3 bits, because 2 to the power of 3 is 8.
So now we have 0, 0, 1 to represent the quantity of 1, which is the most significant octal digit, not counting 0, which is a prefix. And then we have 0, 1, 0 being the 2, but this only accounts for 6 bits. We need a multiple of 4, so we can add 2 more significant zeros to turn this into a byte. This is the least significant digit in hexadecimal. This is the most significant digit in hexadecimal. That's a 0, that's an A, because it's a 10. Okay, so 0A is the next byte. Okay. The next line has a whole bunch of dot words. Okay, the first one is 34 in decimal. 34 in decimal is 22 in hexadecimal because 34 is 2 times 16 plus 2. Okay, that's how I can do the conversion just kind of in my mind without actual calculation. The next one is, oh, wait. If you think the next one is just 3, 4, we're forgetting something. Because we have dot word here, which means each item is going to use 16 bits to represent it. So we need 16 bits to represent 34. 22 is getting the job done already, but we need 1 more byte to represent the most significant 8 bits. So what do we need to do here? Yep, we just have leading zeros. But because of little endian, the least significant byte, which is 22, is the one that has a lower address compared to the more significant byte or the most significant byte, which is the 00. So that is an important concept as well for this homework assignment, is to understand what is little endian, which is the least significant byte has a lower address. The same thing for the 3, 4. There's another 2 zeros here because it is a 16-bit number. 3, 4 accounts for 8 bits. The 00 accounts for the other 8 bits. And then we have an octal number 3, 4, and we'll go through the same conversion process. The number is 3, which is 0, 1, 1, and then 4, which is 1, 0, 0. We've had 2, 0, 0 to the left-hand side. Then we have 1C as the hexadecimal representation. So we have 1C and then a 0, 0 as the most significant byte. Do we have any questions at this point? No questions? Okay. The next thing I'll do is I'm just going to put a L1 here because that's where L1 is. L1 is a symbol. In the assembler, a symbol is just a symbolic name for a particular value, a particular number. That number turns out to be the address of the following byte. Okay, so L1 is a bookmark to say that, oh, the next byte is going to have the address of L1. L1 is the symbolic name of that address. So we have 2, 3 as a long. So we look at 23 as a base 10 number and say, okay, what is it in hexadecimal? We did it already, it's 17. But since this is a long, it will have 1, 2, 3 additional bytes of zeros to use up 32 bits. Any questions about this part here? We're just padding the most significant bits because 17, only takes up 1 byte. We have 3 additional bytes to use up. Then we have 2, 3, which is already in hexadecimal, so that one is pretty easy. And then the last one is a 2, 3 in base 8. So you convert the base 8 2 into base 16. 0, 1, 0 is 2. 0, 1, 1 is 3. And then you add 2 more zeros to the left-hand side. So now you have a 1, 3 in hexadecimal. So we have a 1, 3, 0, 0, 0, 0, 0, 0, 0. Let me just rearrange this a little bit so we can see it all on one single row. Can't wrap onto it. There we go. All right. So these are the 21 bytes that are allocated because of the dot word, the dot byte, dot word, and the dot long. Are there any questions about this part? How many people try to do this by hand first? Very good. And did you verify this is actually how memory was laid out? Okay. So we'll go ahead next to verify this is actually how memory is laid out.
So how do we do that? We're already in GDB. Okay, so we can use GDB. Now this is, when you're in GDB, this is also a good test of, okay, what is L1? L1 is the address of this byte here, which is the least significant byte of the first dot long item. If this is at the location L1, what is the address of this byte? L1 minus 1, 2, 3, 4, 5, 6, 7, 8, 9. So L1 minus 9 should be referring to the address of that particular byte, which also means if I do a X command for examine, X/21BX, I should see exactly these bytes. Is that making any sense? Okay, so let's go ahead and try it. I got some questions, sometimes I get questions like, should I put this here? Should I put this here? And so on. I can understand the hesitation of, oh, maybe I should just put it here and then just do it because, what if it doesn't work, right? But that's the idea. You put it in, if it doesn't work, it will just give you an error. The error itself is indicative of something. That's giving you information that is actually useful, okay? If you don't understand the error message, you can ask me about the error message. But go ahead and try it. So that's the whole point, is to do it using inside GDB. So I'm going to say X/BX, okay? The B is representing a byte. In other words, I'm chopping up memory into individual bytes as opposed to 16-bit words or 32-bit words. So B is 8-bit, X is hexadecimal, and then L1 minus 9 is the start location. Press the enter key. Oh, I forgot one thing. I forgot to specify how many I want to display. So now it displays all 21. And then we go back to the other slide. Okay, I keep forgetting that it's from here. So we compare these two and say, okay, are they the same? I think I deleted the 0C to begin with. Okay, 0C, 1208, 2200, 3400, 1C, 00. And how do we know that this byte is actually at location L1 itself? Okay, what does it tell you about the next line? The next line starts at L1 plus 7. Okay, this is L1 plus 7. 6, 5, 4, 3, 2, 1, 0. Okay. So that's how you can validate the understanding of the memory layout. Because without an understanding of the memory layout, there's no way this assignment can be done. Well, it can be done because there are only 4 billion locations that you can try. Yep.
Like one issue I was having, like I was using IR instead of the print X, so it wasn't padding the leading zeros. So basically when I was manipulating things around, it was really hard for me to tell where exactly I was laying in memory.
Okay. Well, the zeros are always there. It is just the leading zeros are usually not printed.
Yeah, exactly, and I just...
Okay. All right.
Well, noted. Okay.
I was looking at it one at a time.
Okay. Okay, so now that we know how memory is laid out, the next question is, how do we get the 1700 into EBX as the most significant 16 bits? That becomes the next question. So you have to look at this and then look at the 1700 and say, but which bytes am I going to copy to accomplish what we need to do? Because we want 17 to become the most significant byte in register EBX. This is when little endian becomes extremely important, because little endian tells you that if you want 17 to be the most significant byte in a 32-bit register, you want 17 to be the highest address, or the byte with the highest address when you copy. Okay? So if 17 is the highest address and we need 4 bytes, that means we need to roll back 3 bytes to find the beginning. This is the last byte that we want to copy because it's the most significant byte. This is the second most significant byte, which is 1 byte before that one. This is the second least significant byte, and this is the least significant byte. This is the start location of what we want to copy. Is that okay? So far? So what we want to do now is to say, okay, we know where the byte or the address of the first byte that we want to copy. The question is, how do we express it? How do we specify this location? But we already know that 17 is L1. So you just have to go back and say L1 minus 1, L1 minus 2, and L1 minus 3. So the location that I have highlighted on the projector is L1 minus 3. Is that okay? But how do you know that if you copy from this location a 32-bit number, that 32-bit number will end up as 1700 blah 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 blah? How do you confirm that? Well, you can either write it in the code or you can check it out in GDB. How do we check that out in GDB without even changing the program itself? So the key is here not to use your program, use the code in your program as a test platform, because that's kind of cumbersome. You have to reassemble and relink and go into GDB again. You want to make use of GDB as much as possible. So now we are dealing with one thing. A W in GDB is a 32-bit word. Okay, I know that is confusing, but that's how it is. And we want to display as a hexadecimal number. But where we want to start is L1 minus 3, because that's the question. If I start with the byte that is highlighted and look at this byte as the first byte of a 32-bit number, do we end up with a 32-bit number that is 1700 blah 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 blah? This command in GDB will confirm that. And the answer is yes, okay? In fact, we get a 17001C00. It's okay for the 1C00 to be there, even though that is not what we want in the end, because in the end we want 121C, but the other instructions will overwrite it. So we are not too concerned about that. But we will get the 1700 into EBX if we end up copying these bytes into register EBX. Is that okay? So now we switch back to the code, to the actual program, and solve that problem first. So I will get out of GDB, go back into the program, and then we uncomment these two lines, because these are the two lines that are responsible for this, and I will put in just L1 minus 3 here. This line is putting the value of the label, which turns out to be an address, into EAX. The next line, the next instruction, will use EAX as an address. Go to that location and then copy 4 bytes from that location into EBX. So that's why L1 minus 3 is what you need to specify here.
So I checked the first line with the GDB and it had it like 80 something something. So it copied the address, right? Not the actual content, but copied the address.
Okay, so remember, how many people got an email from me today as a reminder, da 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 da?
Yeah, I tried to check it.
You didn't check it. Okay. That was the instruction. I sent out a reminder because some people, already put in the code, they hard code the entire address and go like, no, that's not what I want. I want you guys to do it in a different way. So that's why I send the reminder. Go like, nope, you have to make sure that your code will work in my case. Okay? Because depending on the platform, depending on how you configure the linker, that location can change. The whole thing can float around and change. The only thing you know is it is L1 minus 3. But where is L1? That can change. Okay?
But that number that he gave me was the address, right?
Yeah.
The address.
Well, it's a number. You are using the number as if it is an address, correct? There is no such thing as type in assembly language programming. But you are using a bit pattern as an address. Okay. All right. So that answers the first question. Okay, so assuming that answered the first question, we move on to this particular line here. BX is, how does BX relate to EBX?
because after all, I want EBX to end up with a particular value, so here is a BX, what does it do? It's the least significant part of EBX, right? Because when you say first or second half, then it depends on, are you reading it from left to right, or are you referring to the memory location? So it's a little bit more ambiguous. So we will refer to BX as the least significant 16 bits, or bit 0 to 15 of EBX. So that's a more accurate way to describe it. Okay, but you're right, that's basically what it is. We want that to be, let me pop up my little post-it here. We want that to be 121C, okay? And you look through the memory layout here, you don't see 1213. I don't see 1213, or 1C, 12, because remember we have to flip the order because of little endian. So we don't see 1C, 12. We see a 1C over here, but there's no 12 over next to it. That's okay, okay? That is okay because the next instruction is going to override BH anyway, okay? So I'm not too concerned about BH when I move something into BX. I just want to make sure that BL is correct. So that means I just want the 1C here, which is this byte here. This is L1, this is L1 minus 1, this one is L1 minus 2, okay? So we know the start location to copy is L1 minus 2 to copy into BX. So we go back to the program. Oops. Go back to the program, and then we say this is L1 minus 2. Because this instruction is treating whatever you specify here not as the actual bit pattern to copy, but as the address where you go grab the content to copy to BX. That's the difference between this instruction and the instruction that is 2 lines above it. Is that okay? So L1 minus 2 answered this question. And then the last one is actually the easiest. The last one, which is this one here, is just letting you specify. Whatever you specify here will become BH. But how does BH relate to EBX? Is bit, nope.
The most significant.
Is bit 8 to 15. Yep, it's bit 8 to 15 of EBX. We already know that should be a what? 1, 2? So that means we just specify in hexadecimal 1, 2 here, and that will get the job done. So to get this homework assignment done, you have to put all of these concepts together. Little endian, how memory is laid out in memory, the 3 addressing modes that we have talked about last Thursday and also this Tuesday, and that's basically it. And also the applied reasoning to combine all of that stuff. Okay. Are there any questions about this homework assignment, everything that I have talked about up to this point? Yep, go ahead. Oh, I thought you had a question. Okay, that's good. Any questions? Are there any questions about this homework assignment? How many people ended up watching the video again, at least once? Okay, very good. I should have monetized it. And sell aspirin or Tylenol or caffeinated products. Well, you don't have to answer this question. Yeah, go ahead.
Go ahead.
No, that's fine.
Well, because basically up until really about an hour ago, I didn't understand that the first move instruction was storing an address as a value in EAX, because I was trying to hard code it, and it kept on throwing it way out of the address bounds and causing segmentation faults
and you did not have enough time to try out 4 billion in addresses.
No, here's the deal. I actually did get it fixed and completed and finished and retard exactly at 7 o'clock.
Okay, well that's good. But that experience, taught you, the content of the class. Okay, all that time is not wasted, because most people think I spent 5 hours, 6 hours on this homework assignment where there are only 3 blanks to fill, okay? It sounds like a really good waste of time, but that really is not the case. I hope that's not the case. Yep, go ahead.
Oh yeah, I spent like 4 hours trying to figure out.
Okay, but did you feel that you don't have to answer me if you say that you don't want to answer, you can just say I don't want to answer, but do you guys feel it's a waste of time?
No, I mean,
It's a very valuable sink of time.
yeah.
You're putting a lot of time into it, but it's not
Right.
quite wasted.
It's not quite wasted, especially when you try to reason it out, okay? You say, okay, I think we can do it this way, and it doesn't work, but even that is useful, okay? Even that is useful because if it doesn't work, it means part of your understanding is not consistent with what the computer is actually doing. Yep.
You like spend like 4 hours, but it only feels like an hour. You're so into it, it's like you check your clock for like.
It was just that one idea that just.
Okay, so that's a good point because this particular homework assignment I think really test and tell yourself what kind of a person you are with respect to this class. Okay, I don't really care about the rest, but as far as this class and programming classes are concerned, if someone is doing this homework assignment and feel it's okay, I can work this out and actually spend time to do it and not feel frustrated or feel angry, okay, when things do not work out, those people have a pretty good chance of becoming a good developer because they are just really I'm solving a problem. I'm just going to spend time to solve a
What
problem.
about slightly annoyed? What about slightly annoyed?
Slightly
Very
annoyed is
annoyed.
probably normal, okay, when things do not go your way for long enough, most people will feel slightly annoyed, okay, that's okay. Did you end up destroying your monitor? Okay, so the monitor doesn't have a hole about the same size as your fist, right?
Not the new one.
Okay, not the new one, okay, very good. Not the third one, right? On the other hand, if you feel, okay, I just spent 4 hours on this homework assignment, and it did not even feel like 4 hours, it felt like half an hour, okay, as opposed to 4 days. It felt like half an hour, or I enjoy doing this, then you are destined for work related in development. In fact, I think for people who felt energized by doing this homework assignment and having to kind of put all the pieces together and reason it out, you will become a very good person for information security. Because that requires a lot of problem solving skills, and this is what it is. It's problem solving skills. Okay, are there any questions? No questions? Okay. I didn't bring my roll sheet today because I can probably tell from the missing names, what kind of people, felt so, angry and so agitated that they could not even come to class today. All right, so that's this homework assignment, and I just want to use this, to kind of let you guys know about all those things. And okay, here's the other thing. Someone, also read the notes. Okay, it's already here. Okay, the addressing notes, everything that you need to know to answer the questions. Even if you missed Thursday and Tuesday, if you have been reading the notes in the order, you would have read about it already. Okay, but it's not nearly as good as the in-class demonstration because if you're not seeing the interactive demonstration. But it is here anyway. So addressing notes and memory allocation, is actually the topic that you need to read before you do the homework assignment, and that's why it's positioned right there. How many people read it? Quite a few. Very good. Good job. Just because I didn't mention it doesn't mean that the notes is not useful. It's up here as a link for a reason, right? Okay. So last time I did promise you guys that I would turn you guys into. Oh wait, we need to do the practice test. Okay. So let's go do the practice test. Your practice test is not going to be the same as the previous semester because of the way I reordered the topics. So it will be a combination of 2 in this case. So we'll go back to the main class first. Go back to.
Yep. While you do that, What was the purpose for the last stuff or the stuff past the check here part in the program? Was it just so that way people don't accidentally run through it before checking to see if
No,
the
it's
program
for
did?
my convenience.
Yeah, I guess I saw that and I didn't. Oh, I mean, I understood what it meant for the most part, but
No, that one's for my convenience. Let me try to find my exam first. Okay, I probably have put it onto my Google Drive, but let me answer your question first. It's an interesting question. The question is, what is this label doing here? Check here. So the way I grade your homework assignment is I would download all the submissions of the entire class as one zip file. And then I have a script that will unzip that file and then will turn into individual tar.gz files that you guys turn in. And then it will, for each tar.gz file, it will uncompress it. And then it will find the file name, okay? I think it's bunny.s, okay? And then it will go ahead and assemble, link, and run GDB on that file. I have a script that runs in GDB to put a breakpoint at check here, and then I will compare EBX with the actual number that is expected. And then my script will also include your program into the log file along with the result of your program. So if it is correct, I'll go check your actual code, okay, to make sure that you are not changing any one of the addressing nodes, and based on that, you receive the points. Okay.
How does it identify the file?
Sorry?
How does it identify the file?
Bunny.s. It will search through everything that is expanded and look for the name bunny.s.
No, to be my submission or someone else's submission.
Oh, because I only untar one file at a time. The tarball itself has your name as a prefix. So that's how I can, grade each submission individually. Okay. So that was a good question. I like the observation. Hey, that label doesn't seem to be doing anything here. No one is jumping there, and it is not exported. Why is it here? It's for my convenience. When I grade it, I can now use a semi-automatic way to do it. Full automatic is still illegal in the state of California. And I can only grade 10 at a time, yeah. Oh, that's another good question. Okay, those three we will never really get to. These three lines are equivalent to exit 1, or exit 0, sorry, exit 0 in C and C++. So it will exit the entire program correctly. Because every program needs to terminate correctly. And you don't have to worry about that in C or C++, because when main returns, as far as you are concerned, that's the end of the entire program. But main actually returns to some startup code that ran before your program starts. And that code is responsible to clean up and eventually do this to exit a program. In assembly language programming, we don't have that code before main gets control, so you will have to request the operating system to terminate the process, and that's what that does.
So that's why in GDB, if you say you ran some test ones that were separate and didn't have that stuff and tried to exit the
And then it will crash after that.
Yeah.
All right, good observations. So let me go back to the practice test. So I put all that stuff into my Google Drive. cisp310. And they're organized by semesters. I'm pretty proud of myself, staying a little bit organized.
How did you get 2 terabytes?
Huh?
How did you get 2 terabytes?
I also back up the servers. And somebody told me from district that they say, well, there's no limitation of how much stuff you can put onto the app's drive. So I just say, well, since I'm backing up my the servers, and it's school related, right? So I just push everything up and never delete anything.
Well, if you got a virus like 3 or 4 pushes back, you're good.
Yep. Especially that drown vulnerability. All right, so this is the test, this is the exact test from last year. I will only use a portion of this and a portion of exam 2 because the topics that we have covered is not exactly everything here, nor everything in exam 2 in the previous class. This is still relevant, okay? You know, the time has changed, obviously. Room has changed, but this part has not changed. It is open book and open notes, but no electronics. Are there any questions regarding this part of the test?
So you can bring anything that is either handwritten or printed prior to the class. If you find a good textbook, bring it with you, okay? If you take really good notes and you think that's going to be helpful, take it with you. If you look at certain screenshots of the recording and say, oh, that seems to be pretty useful, take a screenshot, print it out, and bring it with you. You look at all the previous homework assignments, you look at my solution, you think that's useful, bring it with you, okay? So anything that is on paper that is prepared prior to the test, you can bring it with you and use it as a resource. Is that okay? But you cannot share resources when we are in the exam. Okay, so you can, if multiple people, a group of people work on, study together, you come up with the same material for the test, make copies. Okay, then each person can bring that person's copy to the test, because I do not want people to share a single copy during the test. Is that okay? All right. Okay. This is an individual assessment. Did I go through this already? No? Okay. It's an individual assessment. Everything is individual in this class. The score should reflect the competency of the student with the name and student ID as indicated above, which is up here. And unfortunately, most people do not read the instructions and they put first name first and then last name next. Okay, I want your last name first. And that's why I also explain what it is. It is also known as your surname or your family name. So in my case, that would be Aoyang, not Tak. Answers should be independently or originally derived in the allotted time, observing all the rules applicable. No sharing of open book notes material during the exam, and do not discuss the questions with students who may not have taken the exam. Use additional sheets of paper if necessary, which means if you think that you might need additional pieces of paper, you have to bring that with you. Okay, binder paper works, okay? Napkin, not so much, because that's going to jam my scanner. Write legibly. I cannot give points to answers that I cannot interpret without post-exam explanation. In other words, someone can give me some blob of ink and say, well, that's what I meant after the exam. After I explain the correct answer, that person comes back to me and go like, but that's exactly what I meant here. It's a blob of ink. So if I cannot interpret it when I'm grading it, I cannot give points to those answers. Questions have equal weight. Okay, this is a typical thing that I do, which makes your job easier, because what you need to do is to look through all the questions, pick out the one that is the easiest. Do it first. Okay, always get the easiest questions first. This exam, there are 4 questions in the previous one. I might change the number, but they will all have equal weight. This exam accounts for 20% of your final grade. Okay, so moving on to the actual exam here. So this is a gate question. We have 2 1-bit adders. X and Y are both 2-bit input. X plus Y is a 2-bit output, which is this one here. C in is a 1-bit input. C out is a 1-bit output. So C in is here, C out is here. Show all combinations of values of X, Y, and C in, so that the wire M, which is the one connecting the output of the carry out of this adder to the carry in of this adder, is a 1. Okay, first of all, do we understand what the question is asking?
You just have to find the error.
So like, is this one of those disjunctive normal forms kind of deals?
No.
Sounds more like a truth table.
It's more like a truth table. Very good. Okay, it's more like a truth table. You can brute force this. Okay, in fact, it's not difficult to brute force this one. So what you do is you come up with all the possible combinations. Okay, how many inputs do we have into this particular circuit? There are 3 inputs, right? There's C in, there's X, and there's Y. So all 3 are inputs into this particular
circuit. Okay, so let's actually do it. I'll do it here. I'm going to use my notepad to do this one. So I'm going to get rid of the stuff from the previous class and focus on this one. So we say Cin is a variable, X is a variable, Y is a variable. I don't even care about the result of the entire thing. I just want to know what is the bit M, because I want that to be a 1. Cin is 0, 0, 0. So if it's 0, 0, 0, will there be a carry into the second digit? No. Very good. So what M really is the carry from the least significant digit to the other digit. And I think most of you already know the answer. If you have no more than 1 1 on a row, it won't trigger the carry. If you have at least 2 1s on a single row, it will trigger the carry. So that means, if you look at the truth table, I'll just do the whole truth table here. And I'm just gonna copy and paste it. Turn all these into 1s. Okay, there's only 1 1 here, so that will still be a 0. That will be a carry here. There will be a carry here, there will be a carry here. So that means for the answer, you have to answer the last 3 rows. When Cin is 1, X is 1, Y is 0, there M is going to be a 1. Oh no, M is 1? Oh yeah, you're right. X, Y being 1s, and the carry being 0. Okay, you're right. So 1 1 here. So there are 4 rows that will turn M into a 1. Those are the combinations. Yep.
But isn't X and Y a 2-bit input? So it would be like 2 bits each side.
Oh, you're right. Okay, X, Y are 2-bit inputs. So that means, okay, if X and Y are 2-bit inputs, then you analyze it a little bit differently, okay? Because then the truth table is going to be a little bit too long to deal with. So you ask your question, if X is a 2-bit input, Y is a 2-bit input, and then you have a carry, what will give you a carry, after adding just 2 bits? In other words, your question becomes this, okay? You have AB as 2 bits, and then you have CD as 2 bits, and then you have this one here as a carrier. Probably should not use C here. Turn it to an E. Turn it to an E. You have an external carry. So this time you have 5 input bits. Okay, you're right. Okay, I did not read my own questions carefully. Okay, so now the question is, when are you going to end up with a 1 over here? That's the question. But there's actually a very easy way to find out. Because that carry is basically saying the result cannot be stored in 2 bits anymore. 2 bits will only give you the ability to store up to 3. Because 1 1 is 3 as a value, right? So if AD as a value plus ED as a value will give you a sum that is 4 or more, then that carry is going to be a 1. So now you just have to figure out all the combinations. Okay? So the combinations is going to be, okay, this is X and this is Y, it's symmetric. When X is 0, you cannot make the carry happen. Because 0 plus 3 is only 3, so it cannot happen. When X is 1, Y can be 3, and the carry will happen. When X is 2, Y can be 3, can be 2, can be 3, and both will make the carry happen. When X is 3, Y can be 1, can be 2, can be 3, and all of those will cause the carry to happen. So these are the combinations: 1 3, 2 2, 2 3, 3 1, 3 2, and 3 3.
But then would it be considered a Cn?
Oh, the carry. Yep. Okay, there you go. So we have C in here. So once you add C in, then the 0 would also trigger that to happen, because now you have this, and then you have the. This one would 0 or 1 would do it. 001 will do it, and 001 will do it. Yep.
So should we like make another table like that for the like y, or will that like take care of any case for y also?
Any case of y.
Like for example, if y, like what cases?
This gives you all the combinations already. It's just that it's in a condensed format, because this row gives you two combinations. X is 1, y is 3, C in is 0. And then the second combination is X is 1, y is 3, C in is 1. But there are more combinations now, because you also have 1, 2, and then the 1 here. And then you have a 2, 1, and then the 1 here. And then the 3, 0, and the 1 over here. So you have a little more combinations because of carry. Yep.
On the circuit though, is that a splitter? Will it actually send 2 bits to the adder, or 1 bit each one?
It is a splitter. It is splitting. Oh, okay. Okay, so I stand corrected. The original solution is correct. Because I was thinking, that's going to be a little bit hairy, as a question in an exam. So you're right. Because of the splitter, this is X. The bit 0 goes here, bit 1 goes here. So we are still just dealing with the first case. So this answer applies. Okay, thank you. All right. Any questions about this one? Okay, part B is in this diagram, so there's a part B to it. There are two 1-bit full adders. X and Y are both 2-bit inputs. X plus Y is a 2-bit output. C in is a 1-bit input. C out is a 1-bit output. Show all combinations of X, Y, and C in, so the Y X plus Y is 0, 1. Okay, so what it's asking is, I want the result to be a 0, 1 here. So show me all the combinations that can make that happen. What do you think? Okay, let's figure it out. Okay, so here's X, here's Y, and this is C in, and I want the result to be C in, regardless of whether there's an extra carry or not. 0, 0, 1. That will make the 0 and happen. X is a 2-bit number, Y is a 2-bit number, so we have to look at 0, 0, 0, 0, and then C in is 1. And then you have 0, 1, 0, 0, and a 0 here. 0, 0, 0, 1, and a 0 here. So these three are fairly obvious that they will give you a result of a 0, 1. What is not so obvious is you can have situations where it will give you a carry at the end, and it will still give you a 0, 1 as the actual answer. So I'll tell you exactly which one we're talking about. 1, 0, 1, 0, and a 1 here. Because what happens with this case is you have 1, 0 plus 1, 0, and then you have a carry in of 1. 0 plus 0 is a 0 with no carry. 0 plus 1 is a 1. And then you have these two 1s added to a 0 with a carry. 0 plus 0 is still a 0. So you still get to the binary bit pattern of 0, 1 as the result, even though the inputs are 1, 0, 1, 0, and then the carry in is a 1. So now you have three more cases, because you have 1, 1, 0, 0, 1, 1, 1, 0, and a 0. Then you have 1, 0, 1, 1, and a 0 here. So these 6 combinations will give you that particular answer. All right. Any questions about this part? Is that okay? All right, moving on to question number 2. Borrowing the concepts from the hardware multiplier of unsigned values. Okay, this one does not apply because we have not done that homework assignment. We haven't done the hardware multiplier. So Q2 does not apply in this class. Here's Q3. Q3 does apply to a certain extent, but not the way I asked the question. First of all, have we seen this picture before? Okay, we have seen most of it, okay? We have seen most of this picture before. In fact, it is exactly the same picture as this one here. And here are the actual instructions or the things that I want to do. I want to store whatever the program counter is pointing to with a post increment into the address register. How do we do this? So I want you to write down the clock sequence to do it, which means you have to tell me the first thing we have to do is to set those particular bits to 0, 1, and then we do this, and then we do this, and then we do that. Okay? Have we done anything like that before? In fact, have we done exactly that before? Yep, last Thursday. Just last Thursday, we have done exactly that sequence. So what you need to do is to describe it in text. Okay, so you refer to the names. So if you want to be sure, you can basically say RAM cell has to be a 1, RAM load has to be a 1, and so on. So you basically have to name all the pins and specify the big pattern of the pins that are relevant for this particular operation. Is that okay?
Would we also have to put it in the correct order?
You have to put it in the correct order. All right, so let's go ahead and do this one here, and let me see how you guys think of the solution. Okay, so I want PC++ to be stored into, and then the whole thing, stored into the address register. This is a post increment, so it spells out several things already. Let me zoom in a little bit so you can see a little bit better this part here. In order to use the auto increment feature, we want the output of the adder to go back through the mux into the input of the PC or the program counter. So that means the mux has to be configured properly, which also means PC in cell has to be a 0 in this case because this is input 0. So in your answer, what you need to do is to specify just that. You say PC in cell needs to be a 0. And then you have to say PC enable has to be a 1 because we are about to change the program counter. But we are not going to clock yet. So we specify the clock is going to be a 0. It will be clocked later on. We also want the program counter to go through this mux here to drive the address bus of the RAM module. So you look at the input into the mux, and this is input 3 of this particular mux, which is controlled by address driver select here. So you have to, in your description, you will have to say that also. Let me make this smaller so it will fit. So now you say the address driver select is going to be a 1, 1 because it is 3, but since this is a binary bit pattern, if we put a 3 here, I will still count it as a right answer, but 1, 1 is the actual binary representation. All right, so now that we have the correct address presented onto the address bus, we have to go to the RAM module and say, okay, now what do we do with the RAM module? It would have selected the right location. RAM is already selected. You don't need to clock because it's a read operation. You can also say clear, the clear signal here or the reset pin is clear. Okay. I can let you assume anything that you don't specify is a 0, so that will make it easier. The output from the data bus has to connect back to the address register, which is already connected. It doesn't have to go through a mux, but in order to update the address register, you have to enable the register itself. So you have to say, in this case, you have to say address register enable has to be a 1 because then only then it can be updated. All right? Any questions about this part? So at this point, what have I done? Okay, I turned the reset pin into a 0. Nothing is resetting, just to be sure. I have selected the PC in cell so that it will be auto incrementing, but since it's going to do it on the falling edge, so nothing is going to happen at this point. PC enable is a 1, which prepares the program counter to be updated. The clock is a 0, and we connect the output of the address bus, the mux to the address bus, so it connects to the program counter. That's what this line is doing. And then we enable the address register to be enabled so that the presented data onto the data bus is going to update the address register. So after this is all set up, then you have to do a clock high because all registers except for the program counter updates on the rising edge. So this clock high will update the address register itself, and then we need a clock low to update the program counter itself, so now it is 1 more than what it used to be. So that's basically what I'm looking for. It's just a sequence of stuff that has to happen in order for this operation to complete. This is just a text description of what we described or what I illustrated last Thursday. I went through exactly that process last Thursday, but I did it inside LogicSync itself. How many people vaguely remember that? Okay, very good. But if you don't remember all the details or the explanation as I go do it, you can just watch the video again, but do it kind of slowly and make sure that you can follow each step. Okay, any questions about this one? Okay, no questions. The next one is, okay, what is this doing? This we haven't done, inside LogicSync, but let's just take a look at this code here. This is pseudo C code. What is it doing? What is it doing with register B? Register B is providing the content, right? What is getting updated? The content in memory at the location that address reg is pointing to. Okay? Which is not something that we have done. We have done exactly the opposite. The demonstration last Thursday did exactly the opposite, which is the register is getting updated by the memory location where another register points to. So let's go ahead and do this one here and see how we can specify the operations. Okay, so that's for the first part. So the second part, the first thing we need to do is to make register B, which is register 1, in the register bank as the output. So we go to the register bank, which is this component here, and we say, okay, how do we make register 1 to serve as the output? But I don't want it to be just any output. I want it to be the output to the data bus, okay? And if you trace the lines, the address bus is this wire, which goes all the way to here. It goes through a mux into the input register, but it also connects to this wire to go into reg 0 as the output register. So reg 0 out is what we need to configure to have one of the registers inside here to serve as the output of the register bank. So the code or the operation that we need to specify is to say, assuming all the other registers, everything else is being 0, we say reg 0 out enable is a 1 because we need to enable reg 0 out of the register bank. Then we say reg 0 out cell, the selection, to be the register that we want to be the output. Reg B is the same thing as reg 1 or register 1, so that means this is 001 to select the right register. So at this point, the content of register 1 in the register bank is going to drive the address, the data bus. So now we need to configure the memory to read whatever is on the data bus and put it into a certain location. So now we have, I forgot to specify that. Okay, so we have RAM cell equals to 1 to select the RAM. I forgot to put it here. So RAM cell is 1. And then on On this one, load should also be a 1 because it's a read operation. This is a write operation, so RAM load should be a 0. Okay? So now I have set up the data on the data bus. I have selected the RAM and say this is going to be a write operation. But I haven't specified the address bus, okay? Who's going to drive the address bus? So now we have to go to this mux that controls who drives the address bus and say, oh, we want the address register to drive the bus this time. You look at the output of the address register, it goes to input 2 of this mux. So now you have to specify that ADDR address driver cell selection is 0, 0, 1, 0. Okay? So we will take input 2 to become the output. So the address register is now going to drive the output. If I tell you that you can make the assumption, unless you say something is a 1, everything is 0, you don't have to worry about the address register getting updated because it is not even enabled. Okay. So let's check the instruction. What else do we have to do? All right, so that should be it. So the next thing we have to do is just to give the RAM a clock high because the transition will update the content of RAM. So we say clock equals high. And because we assume everything is low to begin with, so there's no need to specify clock low because it is already assumed to be low. So this is unnecessary. We don't have to do that. And that's it. That specifies the operation. It doesn't clean up the bits, okay, but it will do whatever is necessary to get the requested part done. Are there any questions about this part? No questions? Okay. The LogicSim schematic has not changed from last semester. So this is still the same diagram as what we have this semester. All right. So in this case, I give you a huge big old table to make it easier. Because now you can just go to the right part, put a 0, put a 1, at the correct places, and that makes it so much easier. Is that okay? Is that easier, or do you like the other way? Do you like this method, or do you like the big huge table?
I like Notepad.
You like Notepad? Okay.
Tables here.
It's just bigger. There are a lot of bits that you don't have to deal with.
A lot of boxes.
A lot of boxes, correct. All right, so that's one question. I think that's, okay, here's question number 4. So step by step, figure out the 64-bit of this we haven't talked about. Question number 4, we will cover that in this class because it's part of the curriculum, but we won't do it just yet, okay? But according to most students from last semester, question number 4 is one of the hardest questions of this particular exam. So you guys are not getting that one. Okay, any questions about this? So remember, yeah, go ahead.
So on the test, it's just 4 questions.
4 or 5, depending on the difficulty of the questions. The more questions is not necessarily worse because you have more to choose from as the start question. And if you miss one, it's not going to be. It won't take out a lot of points. Hmm?
So like each question is worth what, like 20 points?
Well, they're equal. They're equally weighted, and the entire exam is 20% of your final grade. So if I only give you 4 questions, each question is worth 5% of your final grade. All right, but
That question is 1% less.
okay, but remember I said this is not the only exam because we will also be borrowing something from the second exam of the previous class, and that has to do with me reordering the topics of this class. So this one, I probably won't deal with this. Okay. It doesn't have an example. That would do it. Close to. Okay, that's close to what I would ask. in your exam. So it's the same thing as the egg hunt homework assignment, very much similar to that one. This one has the extra stuff of adding, okay? You know, the only instruction that we haven't really talked about. In this case, there are several things that your homework assignment doesn't deal with. Your homework assignment does not have anything like this. Let me magnify so you can see a little better. Okay. Your homework assignment doesn't have an add instruction in the middle of everything. But what is that really doing? If you look at the context of this add L or add long instruction, what is it doing to BAX?
Pushing the address 4 bytes.
Not pushing, it's just adding. Okay, it's literally just adding the value 4 to whatever is already in EAX. What is in EAX at this point? Look at the previous instruction.
The address
That one itself is an address.
So 32 bits after.
So EAX becomes just L1 plus 4, right? Because it was L1 before, and you just add 4 to L1, so it is L1 plus 4. Is that okay? All right, so this is one thing that we haven't seen in your homework assignment, but we have talked about the add instruction. Did I say that add instruction will not be in the exam? I think, yeah, I did. Yeah, so I won't give you the add instruction, but that's one thing that you haven't seen. The other thing that is even more mysterious is this one here. A dot in is the same thing as a dot long, so just look at this as a dot long. So it's a dot long L1 plus 10. What is that doing? Okay, first of all, let's think about it individually. What is a dot long? What does it mean? What does it tell the compiler?
To allocate 32 bits.
To allocate 32 bits and initialize it, right? And it will initialize it based on the expression that you provide in a dot long. So the expression here is L1 plus 10. What is L1 again? L1 is a label, okay? And the label in this case is defined to be, is the address of which byte, which specific byte? Tell me the nibbles or the representation of that byte. The RS. RS, not PQ, because of little endian. Okay, because PQ is the higher byte in PKRS, it is the second byte. The first byte is the RS. So the address of the byte RS is L1. So L1 is really just an address. L1 plus 10 is another address. That's all it is. It's just another address. Can I store an address in memory? Yeah, there's no reason why I cannot store the address in memory. And that's basically what this is. But there will be a question similar to this one without the add instruction, but it will still be exercising the addressing modes that you have already used in the homework assignment. So there'll be another mini egg hunt in the exam. But because you already understand the concepts, it's not going to take another 4 hours. Hopefully not, correct.
It's gonna take 6 hours.
Let's hope not. So are there any questions about the scope of the exam? So it'll be everything up to all the concepts that you need to do the homework assignment, the egg hunt homework assignment. Okay. Any other questions related to the homework, related to exam 1? Yep.
How much time do we get?
You get the entire class period, so you get all 80 minutes. Yep.
What about the lab afterwards?
The lab after that, I would like to use it to talk about the solution, so that way I'm not going to use lecture time the following day to talk about the solution. So that's what I would do at the lab. I know some people want to go home, and you can go home. I will probably record it, but if you're not there, you cannot ask questions. Okay, so if you want to be interactively asking questions, like how many points are you going to take off if I answer it this way? Then if you want to ask those questions, then you want to be there. Okay, if you think, okay, I can just watch the video and and understand the answer that way, you probably don't have to be there. Yep.
So if like we go, right, can we wrong?
No, the correct answer is not based on voting. The allocation, most of the time is already determined, how I allocate the points. Any other questions? Yep.
It was partial credit, right? Or is there?
Most things have partial credit, to the extent that it is possible. For instance, for a question like this, okay, let me see. I might have put in okay, for this question, these are the answers, okay? What I type here next to each line, that's actually the answer. So if in this case, if on certain lines you get it right and on certain other lines you got it wrong, I will give you partial credit for the ones that are right. Okay? Even if it has downstream consequences causing the entire, the final result to be wrong, but if part of the steps are correct, I will still give you partial credit for that. It's basically based on, from your answer, can I tell that one, you understand the concept perfectly and you apply the concept perfectly without any mistake. That's an A answer, okay? Like A letter, GPA A. If you answer the question and I can see from your answer that you understand the concept for the most part, but you make some mistakes, some typo or some other mistakes, that's a B type of answer. The C type answer is I can kind of see that you get most of the concept, the core part of the concept, but there's lots of mistake or omission. That's a C. A D means I do not see sufficient understanding of the concept. That's a D, but there's some answer that is related to the concept, but it's not right, okay? That's a D. A missing answer or something that's completely wrong is an F. So that's how I will grade, these questions. The more partial steps you show, the more chances or the more evidence I can look at and go like, okay, I can see this is indicative of, okay, this person at least understands this part, and I can give partial credit for that. Is that answering the question? How partial credit is assigned? Okay. Any other questions?
Answer all the questions?
Well, you want to order your answering, deal with the questions that you are most confident first. Because if you try to answer the questions in order, and the first question turned out to be the most difficult one for you, may not be for the entire class, then you might end up using 60–70% of the time just answering the first question. Then you answer the other questions, and then you find out the last question turned out to be the easiest from your perspective, but you're running out of time already. So you don't want that to happen. You want to scan through all the questions and just evaluate and say, okay, this one seems to be the easiest. Deal with that one first, and then deal with the second easiest. So this way, when you do run out of time, you'll be running out of time on the most difficult question, which has the same weight as all the other questions. So that would be the best trade-off, the best use of your time, so that you can end up with the most points given the amount of time that you have. Okay, does it make sense? Yeah, okay. All right, so what I'll do is I will stop the recorder and then we'll go to the lab. And if you guys have any questions about this homework assignment, make sure you ask those questions, okay? That's how you can use my lab time.